Hello everyone. My name is Anand Bangar, a student of third year BTech in software engineering at MIT Academy of Engineering, RNG. Today I'll walk you through one of the most fundamental concepts in machine learning, that is how we find the best fit line in linear regression by optimizing the loss function using gradient descent. This is a core technique in exploratory data analytics and the foundation of modern AI. So let's dive in. So first, linear regression. Linear regression is a basic yet powerful statistical method used to predict a continuous output like price, temperature, or sales based on one or more input features. In its simplest form, simple linear regression, we just use one input variable x to predict the output y using a straight line. The equation is y cap is equals to mx plus c. Here m is the slope, also called weight. It tells us how much y changes for a unit change in x, and c is the intercept or bias, the predicted value when x is 0. Our ultimate goal is to learn the best possible values of m and c from the data so we can make accurate predictions. So now, why do we need a best fit line? For this, imagine you plot your data points on a graph. You could draw infinitely many lines through or near them. But which one is truly the best? Relying on visual guesswork isn't reliable, especially with noisy or high dimensional data. So we need a mathematical objective way to measure how a line fits the data. That's where the loss function comes in. A loss function quantifies the error between our model's predictions y cap and actual values y. In linear regression, we typically use mean squared error or MSE. The formula is MSE is equals to 1 by n into summation of yi minus yi cap whole square. So why do we need the squared error? There are three main reasons. First, squaring makes all errors positive. Second, it penalizes large errors more heavily, so the model focuses on fixing big issues. And third, the function is smooth and differentiable, which allows us to use calculus for optimization. This differentiability is crucial because it unlocks the power of gradient descent. Our mission is clear, that is to minimize the MSE by finding the perfect values of M and C. If we could visualize MSE as a surface plotted against all possible M and C values, it would look like a ball or valley. The lowest point in the ball is the global minimum, where the prediction error is smallest. But we can't check every combination of M and C. That that would be impossible. So instead, we need a smart way to navigate down the hill to the bottom, and that's exactly what gradient descent does. Gradient descent is an iterative optimization algorithm. Think of it as you're standing on a foggy mountainside. You can't see the valley below, but you can feel which way is the steepest downhill. So you take a smallest step in that direction. You repeat this and eventually you reach the bottom. In mathematical terms, the gradient or the slope of loss function tells us which direction reduces the error the most. At each step, we move opposite to the gradient because we want to go down, not up. This lets us converge to an to the optimal parameters without brute force. Now let's see how this works mathematically. We update both m and c simultaneously using these rules. M is equals to m minus alpha into del msc by del m. C is equals to c minus alpha into del msc by del c. Here alpha is the learning rate. It controls how big our steps are. The partial derivatives are del msc by del m is equals to minus 2 by n summation of xi bracket yi minus yi cap. Del MSc by del C is equals to minus 2 by n summation of bracket yi minus yi cap. This tells us how sensitive the loss is to the changes in the slope and intercept. The negative sign in the update ensures we move downhill towards lower loss. Now let us understand this with an example. Suppose our data is x is equals to 1, 2, 3 and y is equals to 2, 4, 6. Clearly, the true relationship is y is equals to 2x. So the best m is 2 and c is 0. We start with m is equals to 0 and c is equals to 0 and alpha is equals to 0.01. Initial predictions y cap is equals to 0, 0, 0. There are huge errors. We compute the gradients. Del MSC by del m is equals to minus 12. Del MSC by del c is equals to minus 8. Then m is equals to 0 minus 0.01 into minus 12, that is 0.12, and c is equals to 0 minus 0.01 into minus 8 is equals to 0.08. Already our line is improving. The MSC drops from 18.67 to about 16.2. After many such iterations, m converges to 2, c to 0, and there is the perfect fit. The learning rate is make or break hyperparameter here. If alpha is too large, our steps overshoot the minimum, the algorithm may oscillate or diverge, and the loss might even increase. If alpha is too small, we take tiny steps. It takes thousands of iterations to converge, wasting time and compute. But alpha is but if alpha is just right, say zero point zero 0.01 or 0.001, we get smooth efficient convergence. In practice, we often start with alpha is equals to 0.01 and tune it based on performance. So let's have a recap. We learned about linear regressions using model data and the equation y cap is equals to mx plus c. The MSC loss function measures the prediction error objectively. Gradient descent minimizes MSC by iteratively updating M and C in the direction of the steepest descent. The learning rate controls step size, balancing speed and stability. Together, this process gives us the best fit line, a powerful tool for prediction. And remember, the gradient descent isn't just for linear regression, it's the engine behind neural networks, deep learning, and most modern AI systems. Thank you for watching. I hope this video have helped you to understand how to use gradient descent to optimize the loss function and find the best fit line.